Welcome to the Cosmic Savannah with Dr. Jacinta
and Dr. Magwela.
Each episode will be giving you a behind-the-scenes look at world-class astronomy and astrophysics happening under African skies.
Let us introduce you to the people involved, the technology we use, the exciting work we do, and the fascinating discoveries we make.
Sit back and relax as we take you on a safari through the skies.
Hello and welcome to today's episode.
Hi, it's Jacinta and Siamiso with you today. Dan's away, but hope we'll have a good time together.
I mean, we are holding it down today with Jacinta.
Holding it down. All right, okay.
Yeah. And on today's episode, we have Sthabile Kolwa, who is a researcher and astronomer at...
And lecturer, yep.
at the University of Johannesburg.
Mm-hmm, yep, UJ.
At UJ, the Orange University. Yeah. Her research work mostly focuses on trying to understand how galaxies are formed, right? And Jacinta chats a lot to her about this. But just before we get into this conversation, I know that galaxies are really, really complicated. Mm-hmm. And how complicated are they, Jacinta?
Very complicated for a lot of different reasons. So one reason why galaxies are complicated is because they're made of lots of different stuff. So there's gas, there's dust, there's stars, there's supermassive black holes, and of course there's dark matter all around that. Mm-hmm. And other than the dark matter, the other things, all of those other components, they all emit at different wavelengths. So you have the full electromagnetic spectrum, which is all of the different types of light. Optical light that we see with our eyes being just one particular wavelength on that spectrum. We have longer wavelengths such as radio and millimeter and infrared. We have shorter wavelengths such as ultraviolet and X-rays and gamma rays. And we need telescopes that can observe each of these different types of light in order to see all of the different stuff inside galaxies and therefore to understand what's going on inside them.
I mean, everything that you've just told us is a lot of information. But, you know, just talking about how complicated galaxies are, definitely the evolution of galaxies is also very complicated.
Yes, well, that adds a whole nother dimension. So the other aspect is not only do galaxies that are kind of close to us, they all look different and they all have these different components, but then also the further away you look, so the deeper into space, the further back in time you're actually looking, because of the amount of time it takes for light from these distant galaxies that are billions of light years away to reach the Earth billions of years later. So we're seeing them as they were billions of years ago. And what we see is that galaxies that are further away look really different to galaxies that are close by. And that means that galaxies used to be different to what they are now. And that means that galaxies have changed and evolved over the history of the universe. So when we look deeper into space, we're seeing all of these different components when we look with the different telescopes at different wavelengths, and everything's changing. So it gets quite a complicated mess eventually.
It does sound really complicated. I mean, I've always said that sometimes astronomy feels like we're looking back at time. And I think just what you just said just highlights that and touches on that. You know, normally at school, I think I've seen this while I was also still at school, that, you know, we learn of 3 different states of matter being gas, solids, and liquids. And we know that gas is like the hot gas and like, you know, as hot as it gets. But, you know, sometimes when we are just talking about galaxies, all of a sudden we hear about cold gas. What is that?
Yeah, so cold gas is actually a really important part of a galaxy. And it's important because that's what stars actually start forming out of. So out in space, you can get incredibly, incredibly cold temperatures that you can't really get to on Earth very easily.
Like how much?
Like more than minus 200 or 300 degrees. So really, really, really cold. And it's only in those conditions where it's cold enough that 2 different hydrogen atoms can join together to form a molecule. So if 2 atoms join together, it's called a molecule. And this is called a hydrogen molecule. And that's important because it's from this hydrogen molecule, big clouds of this molecular hydrogen gas, where hydrogen fusion can finally begin, and that's what a baby star is. So in order to form a star, which can create heat and light, you actually first need it to be in a really, really, really cold environment. And so we need this sort of molecular gas in order to form stars. So yeah, it's not really intuitive that gas can be really, really cold, but actually it can be. Yeah.
Yeah. And so what kind of telescopes then do we need to actually observe this molecular gas?
That's a good question. So you can use what we call a millimeter or submillimeter telescope. And we don't often talk about that on the Cosmic Savannah. We're often talking about radio telescopes.
Yeah.
Like we've just had all of these episodes on the SKAO and how that's going to be this big radio telescope. But there's actually another telescope called ALMA, which is the Atacama Large Millimeter Submillimeter Array, and it kind of looks like a radio telescope. So it's got dishes. They look a little bit different to radio dishes, but they're more or less kind of the same. If you imagine sort of like a satellite dish, and they're all up at the top of a really high up region in Chile.
Oh, okay.
In the Andes, yeah, above a lot of the atmosphere where it's a lot drier and there's less atmosphere. So this is called a millimeter telescope, and it observes light that's a little bit shorter wavelength than radio light. So a little bit higher energy than radio light. And what you can see with that is you can see molecular gas, and it's such a powerful telescope that you can see molecular gas in galaxies that are really, really far away. So when the universe was younger, and you're seeing the molecular gas in galaxies a really long time ago, back in the past. And this molecular gas, it can sometimes, for example, not hydrogen, but another kind of molecule that's often found in the same regions where this hydrogen molecule is found is carbon monoxide, so a carbon atom and an oxygen atom. And they've been joined together to form carbon monoxide molecule. And these two atoms can kind of rotate around each other and jiggle a bit within this molecule. Yeah. And as it does that, it releases a little bit of light, which is in these millimeter and submillimeter wavelengths. And so with a telescope like ALMA, a very, very sensitive telescope, you can actually see this molecular gas in very distant galaxies. And a lot of that is what Sthabile is going to talk to us about today. So she's using ALMA to try and detect this carbon monoxide gas and other kinds of molecular gas in really, really distant galaxies to try and understand how much fuel for star formation these galaxies actually have.
Oh, that is really, really cool, actually.
Yeah.
And so Sthabile, as you've said, that she'll be talking more to us about this, but she will also be talking about radio galaxies. And I know this is your field, Jacinta, so just tell us a little bit about that again. But
yes.
But
yes.
do not give away too much.
Okay. Yes, that's true. I can just talk forever about this. All right. I'm going to try and keep it real quick. Okay. So some galaxies, well, we know almost all galaxies, we think, have a supermassive black hole in the center of them. Even the Milky Way does. It's called Sagittarius A star.
Yeah.
And black holes are not actually like what you see in the cartoons, like infinite vacuum cleaners that continue to suck everything into space. That's actually a myth. They are just kind of like the cores of dead stars, but these ones we're talking about are like millions or billions of times the mass of the sun. So these are massive, supermassive black holes. And sometimes when gas and dust does fall into them, they can release huge amounts of energy. A lot of weird physics is going on, so we'll kind of skip most of that. But basically what they can do is send out these huge kind of beams of radio light. It's because of it's like it's kicking these electrons out and they're traveling at kind of close to the speed of light, and they're getting caught up in all the twisted magnetic fields, the weird magnetic fields near the black hole. And as they kind of go spiraling out into space, they're releasing a whole bunch of radio light. And so we can see these massive beams or kind of jets. If you think of like a whale's blowhole, and it like sends out a stream of water that's kind of like in a column, and then it just kind of ends up in this big plume. That's kind of what the radio light looks like, and we call these radio jets. So if you've got a galaxy that has this active supermassive black hole with stuff falling into it and it's sending out these big radio jets, we call that a radio galaxy. So Sthabile is looking at these radio galaxies that are really far away, so really far back in time, so when galaxies were younger. and trying to find out how much molecular gas is in those. So how much star-forming fuel is still in these distant radio galaxies, and trying to combine all of those physics to try and understand why and how galaxies have evolved over the history of the universe. So just like no big deal or anything.
It is actually a big deal, but it's also very much interesting. And I think now we'll take the time to actually listen to the interview that Jacinta did with Sthabile.
Okay, I'll be quiet now. Let's hear from Sthabile.
Yeah.
With us today is Dr. Sthabile Kolwa, who is a lecturer and early career research astronomer at the University of Johannesburg. Welcome, Sthabile.
Thank you so much for having me on this show. I'm such a fan. I've been up to date with all your episodes over the years, and it's such a wonderful way to stay in touch with astronomy happenings in South Africa and across the continent, actually, which is all very exciting.
Oh, thank you. We're always excited to hear when someone's listening to all of our episodes. That's great. So thanks for being a dedicated fan. And we're, of course, a big fan of you. So can you introduce yourself to our listeners?
Yes, of course. So I'm Dr. Sthabile Kolwa, as Jacinta said, and I'm a lecturer and new to the field early career astronomer at the University of Johannesburg. And my research interests are in galaxy evolution. Specifically, I would like to understand how the properties of galaxies change with cosmic time. And by properties, I mean the star formation rates, how quickly galaxies form stars, how quickly they're able to accumulate stellar mass. The galaxies that have supermassive black holes at their centers, how do these objects affect the evolution of the galaxy with cosmic time? How are the different components of the gas, the cold and the warm and the hot components connected? How much of that, in terms of the abundance of the gas, is there? So everything about galaxies and how they change as the universe gets older or younger, whichever way you're looking.
Okay, so just all of the big questions in astrophysics then.
Yeah.
All right. So, okay, we're going to unpack that bit by bit. But let's just start with kind of your story. So how did you get to where you are?
Yeah, so I got to where I am as a result of an early interest in astronomy that began when I was in primary school. And I would enjoy reading, say, popular science books that are tailored for children at the library. And I would go through different topics of geology, animals in the wilderness, marine life, life on the savannah, etc. When I came across a book on astrophysics, it was called Space and Time. And it delved into different concepts that one would be presented with in astronomy, such as star-forming regions or the formation of stars, the stellar scales, how do stars give birth, how are they born? And then up to the galaxy scale, where you've got millions and billions of stars that are gravitationally bound. And what are those objects, and roughly how do they evolve, and what is in galaxies and other objects in space, comets, asteroids, etc. It dealt with all aspects of astronomy, just for the young reader. And I was particularly fascinated by the concept of black holes. The way that was described, it seemed most esoteric in nature, that seemed to be these objects in space that very difficult to explain in terms of what happens within their cores and within their, really, the deepest cores of black holes beyond their event horizons. And I just thought, well, this is a field that has so much potential for discovery. And I would really like to one day be involved in that quest to understand more about the universe. So went through school, of course, continued to have an interest in the sciences and in math, and I did well in those subjects. And at the university level, I eventually, after some trial and error with other degrees, I enrolled for an astronomy program at the University of Cape Town. And I went through that entire track as an undergraduate student and really enjoyed it. It was fruitful. I learned so much. And thereafter, I went to pursue a postgraduate degree and then a PhD. Eventually, that landed me up in Germany, where there were tons of astronomers and astrophysicists who I could speak to and learn more from. And now I'm here after my PhD, continuing to work on research.
Awesome. That's quite an adventure.
Yeah.
How was Germany?
Germany was, I would say, overall wonderful in that I was in Garching, which is quite a hub for nerds. It's quite a nerd hub. In fact, they now have two Nobel Prize laureates within that community, both in physics and astrophysics. In fact, they've got two astrophysics Nobel Prize laureates, at least teams. They've won the Nobel Prize now twice. So clearly, there's plenty of research activity, plenty of people to talk to about observations of various objects in the universe, from protostellar regions all the way up to large scale structures, the voids and filaments of the known universe, and people who work on simulations, people who work on actual telescope observations. You have people there who are designing new instruments for upcoming telescopes, such as the extremely large telescope held by the European Southern Observatory Consortium. And it's exciting to be in a place where you can learn so much from having a coffee chat with someone or going to have lunch with someone.
Yeah.
So it's the best place to be if one wants to learn more and more about astronomy, about the field, and also about the universe at large.
Yeah, wow, it must have been extremely vibrant and excellent for a PhD student to be involved in. All right, so let's get into your research. Now, you said that you study galaxies and galaxy evolution, and so you're interested in studying distant galaxies. Why is that?
So, distant galaxies are quite essential to us in terms of developing a framework of how the earliest galaxies formed or what the conditions were that were ripe for galaxy formation very early on in the universe. So, this is soon after the so called epoch of reionization, when the universe suddenly became transparent to radiation after going through the so called dark ages. There suddenly became the possibility for galaxies to switch on, and knowing what the processes were in this early stage, I think is essential because it's actually a missing component in the story of galaxy evolution through cosmic time. We have wonderful resolved images of nearby galaxies, and we've been able to survey the nearby universe quite well in different parts of the electromagnetic spectrum, such as the radio and the optical, in the infrared, in the X-ray. And so we've got a vast amount of data for that portion of the known universe, but very far out. When the universe was young, instruments were limited and have been limited in being able to see that. And so we need to essentially probe this uncharted region of the universe. And that's why distant galaxies are quite a hot topic in astronomy.
Yeah, definitely. I mean, I couldn't agree more. That's obviously, it's my field as well. So, we had the Big Bang, and then the universe was this like hot plasma, and then it started to cool down, and then it was the dark ages where nothing really happened. And then all of a sudden stars started forming, and then galaxies started forming out of them. And we want to know more about those objects, but they're really hard to detect because they're so far away. As we look deeper into space, we're looking back in time. If we look far enough back in time, we can see galaxies just after they're formed, and that's kind of what you and I are both working on, these distant galaxies that existed earlier on in the history of the universe, which is a mind-blowing concept, but it's really cool that the whole universe acts like this massive time machine for us to be able to see back in time. Okay, so what is it specifically about these distant galaxies that you're actually trying to study?
So our team is very interested in a specific set of distant galaxies known as radio galaxies. So these are interesting objects because they glow very brightly in the radio portion of the electromagnetic spectrum. So they're very different to the kind of normal, regular star-forming galaxies that one would see. They're very special in that regard. And they also have large, fluffy structures known as radio lobes that make them also very specific in how you observe them using radio telescopes. You can actually see these lobe structures. And these structures are known to affect the gas that they encounter, either in the interstellar medium, so the gas between stars, or in the extended circumgalactic medium. So that's the larger, wider gas that envelops the galaxy.
Okay, and what's causing these big radio fuzzy lobes?
At this point in time, I don't think there's a consensus on what forms these radio fuzzy lobes, but the general idea is that you have stuff material falling onto the central supermassive black hole. And as it falls onto this very massive, compact, and dense object, spins around, spins, and forms a kind of disky structure. And through this, there's an exchange of energy from the material into what we see as these large, fluffy radio structures, essentially. So it's kind of think of it as an exchange of energy from the gas that falls onto the supermassive black hole to the large, extended lobe structures that we see using radio telescopes. The actual intricate details of that
we don't know yet.
Under contention, exactly.
Yeah, so it's all got to do with weird relativity near a black hole, how gravity behaves and how magnetic fields behave and all of this strange stuff, right?
Yeah.
Yeah.
That we need to figure out.
Yeah, exactly. Okay, so now you mentioned the gas in this galaxy and around the galaxy. Now you look at the gas in particular. Tell us a little bit more about that.
Yes, so that does form quite an essential part of our research because we are looking at the so-called cold gas. So by cold, I mean minus 200 degrees Celsius, roughly. That's unimaginably cold for the average human being. But these kinds of conditions exist in space, and gas can reach those temperatures. And this cold gas is very important in galaxies because it is the fuel for star formation. So in order for stars to form, cold gas needs to essentially collapse and form what we call star forming regions, where stars are eventually able to begin shining as a result of the collapse of gas. So in these regions, we need to have carbon monoxide. That's a very essential component of the cold gas. And sometimes the carbon monoxide, as you know, is a molecule, so it consists of carbon and oxygen atoms. Those molecules can be dissociated, which
Ooh, what does
results...
dissociated mean?
Okay, so that means that the molecule, by some action, that perhaps due to a photon or a cosmic ray, is able to break apart. A molecule is able to break apart. So that means that the carbon atom would then become isolated from the oxygen atom. And in cases where this happens in the so-called star-forming regions, we are then able to trace light that comes about as a result of transitions, electron transitions in the carbon atoms, as well as in the oxygen atoms. But for us specifically, we were tracing the light that comes from the electron transitions in the carbon atoms.
Okay, so we've got a few physics concepts in there, but that's okay. We're going to break it all down. All right, so you study the cold gas within galaxies. And stop me if I get anything wrong here. Cold gas within galaxies, very cold, minus 200 degrees Celsius or colder, which is where stars form because we need the gas to be very, very cold in order to condense and be dense enough to start forming stars, start the hydrogen fusion. All right, so we know that it's really cold in there, but how do we study that? We can only see it if it emits some sort of light. And you're saying that it does emit light if the carbon and the oxygen of particular molecules in this cold gas are ripped apart by receiving some sort of energy, maybe like they're hit by a photon of light and they break apart. And then those atoms have electrons in them, which can move up and down between different electron energy levels. And when they do that, they emit light, right?
Exactly.
All right, great.
Mm-hmm.
Mm-hmm. Nailed it.
Yes, that's it.
All right. And then, so what kind of light do they emit? We know that there's the whole electromagnetic spectrum. You've already spoken about radio light, which is the very low energy, long frequency that we can detect, and we can see these fluffy stuff from light from the black holes. What kind of light do we have to use to see these molecules?
Okay, so for carbon monoxide molecules, as well as the carbon atoms that will result when the carbon molecules are broken apart, as we mentioned a bit earlier, you would need to observe millimeter wavelengths of light. So millimeter wavelengths of light are very close to the radio in the electromagnetic spectrum. In fact, the so-called millimeter or microwave portion of the electromagnetic spectrum sits right next to radio wavelengths. So that means that when we're observing microwaves, the wavelengths are just a little bit shorter. You can say 100 times shorter than those that we see in the radio, roughly 100 to 1,000 times shorter. And in this portion, we are able to observe that light from the carbon monoxide atoms that exist in the cold gas, as well as the carbon atoms that exist on their own in the cold gas.
Okay, so let's start with optical light, which is what we can see with our eyes. And then if we go to longer wavelengths, lower energies, lower frequencies, we get to infrared and far infrared. And if we keep going, we get to microwaves. And if we keep going, we get to millimeter and submillimeter. And if we keep going, we get to radio, right?
Exactly, that's the correct sequence.
Okay, so it's a little bit millimeter and submillimeter, which is where you're detecting these molecules, light from the molecules. It's a little bit higher energy, a little bit higher frequency, a little bit smaller wavelength than radio, right? But it's lower energy, longer wavelength than microwaves. Is that right?
Exactly. That's correct. So right in between microwaves.
Right. Okay. And presumably it's called millimeter and submillimeter because the wavelength of the light is approximately in the millimeter range, right?
That is correct. Yes.
Yeah. Okay. Well, that makes sense.
Yes.
Okay. And so what kind of telescopes can you use to detect this sort of millimeter light?
So millimeter light can be detected using what we call interferometers, which are arrangements of dishes, what most people would say are
like satellite dish.
Satellite dishes
it looks like that.
Exactly. Large arrangements of satellite dishes that work together, that they observe generally same targets on the sky at a time, and using a clever instrument known as a correlator, each of those dishes are able to work together in concert to form a very detailed image of a distant object. So detailed in terms of us being able to see the finer aspects, the small scale aspects of the object, more so than we'll be able to see with just one of those dishes.
So you get really good resolution, right?
Exactly.
Okay, so it kind of looks like a radio telescope, but just slightly different.
Yes, slightly different in terms of the design of the dishes and the receivers, where the receivers are located, etc. But very similar to a radio telescope.
Okay, well, that makes me comfortable because I'm a radio astronomer, so I know what that looks like. But we're going to put an image of a millimeter telescope on a website so that you can see what it looks like if you're unsure. Do you use one telescope in particular?
So our team has been using one telescope in particular because it is one of the most sensitive millimeter interferometers in the world. By sensitive, we mean it's able to see some of the faintest millimeter light signals in the universe. And that is very important to us because we're observing objects that are very far away. That means we need a telescope that's able to pick up very faint light signals in millimeter wavelengths. And this special instrument is known as the Atacama Large Millimeter Array, and it is run by the European Southern Observatory and the ALMA Consortium, and it is based in the Shenanto Desert, close to San Pedro de Atacama in the country of Chile. And the conditions there are very dry, which is optimal for observing millimeter light because water vapor can be very obstructive when we start observing millimeter wavelengths from space. We don't want essentially the H2O signals from our atmosphere to interfere with our signals from distant galaxies.
So the atmosphere gets in the way.
Yeah. Mm-hmm.
Okay, so you use ALMA, which is the Atacama Large Millimeter Submillimeter Array, which is in Chile, as you said, up on the top of a kind of Andes, I guess, on a plateau up there, where it's nice and high above a lot of the atmosphere, and it'll be drier up there, so less humid, not as much water vapor in the air, so that those annoying water vapor molecules don't absorb our yummy millimeter wave light that was coming from all the way from very, very distant galaxies.
Yeah, exactly. Exactly.
Yeah, Cool. All right. Have you ever been there?
So I had a wonderful opportunity to go to San Pedro, the Atacama in
Did you?
Chile. Yes, yes, it was great. So I spent some weeks as a PhD student volunteering behind the control desk where observations are taken from the
Wow.
for not from the
That's so
ALMA telescope,
cool.
but what we call the Pathfinder of ALMA, which is the Atacama Pathfinder experiment, also called APEX for short. And I spent some time
Ah.
taking observations. It was wonderful. I didn't use the data, of course. There were observations for other
Hmm.
astronomers who were successful in obtaining
Hmm.
time on the telescope. And I did have an opportunity to go up to the site where both Apex and Alma have been constructed. So I saw the dishes, and they are a wonderful sight to see, as always.
Oh, I'm super jealous. That's so exciting.
Yes.
Wow. And what was it like up there? Was it super cold and dry?
Yes, you definitely feel the dryness. Your skin does dry up very quickly, so one does need to have plenty of body lotion with them,
Yeah, lots of moisturizer.
moisturizer. And since the high site for Alma and Apex is at roughly 5,200 meters, one does also feel the thinness of the air, which means
Not
that
much
you
oxygen.
don't have much oxygen. So you're used to walking around and moving about at close to sea level. You'll have a difficult time walking around at the same speed that you do at that site.
Oh,
Yes,
wow.
altitude takes some getting used to.
So you get kind of like out of breath and stuff?
You lose breath very quickly, yes. So you're
Mm,
advised to walk slowly and
mm.
just pace yourself.
Wow. Do you get headaches?
I didn't have any headaches, thankfully. I mean,
Oh, lucky.
yes, I was in. I had good company, as I was told to stay hydrated and move slowly.
Good.
But there are some side effects, of course, as far as
Mm,
altitude sickness goes. So one does need to take care
yeah.
of themselves at that height.
Yeah, so I've been to Chile once. I did an internship at Gemini South Observatory, which is also up in a mountain in Chile, but it's not as high as Alma. It's only about half the height. So I think it's like maybe about 2,500 meters up. But I got a splitting headache,
Oh, sorry.
and yeah, even at that height, I was feeling the lack of oxygen. So it's really interesting. Yeah, like you don't have to go that far up before you're up above a large
Yeah.
fraction of the atmosphere.
Mm, yes,
Yeah.
it is an interesting
Yeah.
experience indeed.
Yeah, but good for astronomy.
Wonderful.
All right. Okay. So what did you find when you used ALMA to look at these millimeter signals from the cold gas in really distant galaxies?
Okay, so our first main finding, the most obvious part of looking through our data, was that the signals were very faint. In fact, they were quite disappointingly faint.
Oh no! Did you
Yes,
find anything?
but thankfully we were able to look through the spectra. So when we have a spectrum, of course, we look at how the brightness changes as a function of wavelength or frequency. So at the specific frequency of this spectral line that we expect from carbon, we were able to see quite thin lines. But they were there, and
Hmm.
that told us that there was a signal, but it was a very faint signal. And based on those rather thin or narrow lines, we were indeed successful in finding a constraint or measure of the molecular gas within the ISM, but within the interstellar medium of the galaxy.
Mm-hmm.
So that told us that there was a reservoir, at least some molecular gas in the interstellar mediums of these galaxies that we observe, but there was not a lot of it. In fact, there was a low
Mm.
abundance of molecular gas. And trying to take that finding and put it into context with what we know about radio galaxies, in that they are objects that they have been seen to have very high star formation rates in some cases, but in other cases, very low star formation rates. And they're also galaxies that have very massive complexes of stars and gas. So they're high stellar mass galaxies, essentially, that's what we would say. So we tried to all of these findings into context based on what previous researchers have seen about radio galaxies, and that they're very massive. They also have these huge radio lobes and jets that put out a lot of energy into the interstellar medium as well as the extended gas medium around them. And we were starting to perhaps think about these sources as objects that form their stars very quickly over very short time scales. So they have vigorous star formation very early on as they evolve. And perhaps as a result of those big lobes that form at their cores, gas might be pushed out of the galaxy. And as a result, star formation will be disrupted and will then eventually turn off due to the loss of cold gas from the interstellar medium. So that was our interpretation. Of course, what helps with, of course, the scientific method is as you receive more and more evidence, you're able to build your case, a stronger case for what you believe to be the correct interpretation. But this is our initial understanding of what may be happening with radio galaxies. So they form stars very quickly and they lose their gas very quickly. And as a result, we won't be able to see much of that cold gas, unfortunately, unless we go further out into the younger, or to see younger radio galaxies, essentially.
Oh, that's cool. Okay, so you are looking at these radio galaxies where the black holes and these jets that they're producing are releasing loads of energy and basically like sweeping gas out of the galaxy and like heating it up so that it's not there or it's too hot to form stars, right? And that's what our idea is. We think that this is called AGN feedback, where it's, you know, this feedback of energy from the black hole back into the galaxy, heats everything up, prevents star formation. And you were looking to see, well, is that true or not? Like, you know, is there any of this cold gas still in the galaxy that has all of this radio AGN, you know, black hole activity stuff? And you found, well, there is actually some, but there's only a little bit, right?
Yes, exactly. Not as much as we expected, but perhaps yes. As far as what you've described as AGN feedback goes, this might be a consistent result with how we understand this process to work in terms of how it can either slow down or completely shut down the formation of stars in a galaxy over time.
Right. Sorry, I didn't actually mean to say AGN feedback. I didn't realize I'd said that. Sorry, listeners. That's a very technical term. Okay, that just means the AGN is active galactic nucleus, which means a galaxy with a supermassive black hole on the center with stuff falling into it, releasing loads of energy, which is just exactly what we're talking about. Sorry, that was a very technical astronomy term. All right, so you said there was even less gas than you were expecting. So why were you expecting more?
All right, so we were expecting to find more cold gas than what we eventually found in these galaxies, because we had observed in a few other similar objects, so similar as in radio galaxies, at similar distances to the objects we were observing, seemed to be very rich in carbon. So they also had massive reservoirs of cold gas. So we thought, okay, if we continue to look at radio galaxies at this distance, we should find more and more of them have this carbon-rich cold gas. But unfortunately, our expectations were defied, as is sometimes the case in research.
Well, that's okay. Yeah. I mean, it's good. You come up with a hypothesis, you test it, and you're like, well, okay, that wasn't the case, and now we have to kind of try and understand why, right? It's all part of science. Yeah. Okay, so, and then And then you also said that, okay, so we'll probably have to look to even further distances, meaning we have to look even further back in time to see radio galaxies when they kind of first switched on. So when the black hole started to have stuff falling into it and releasing all this energy, but it hadn't released much energy yet, we think that there would still be cold gas in there because there wasn't enough time for the black hole energy to heat up the gas, right?
Exactly. I think that is our next stage of exploration, to look at younger radio galaxies and find out if they still have some of that cold gas available, because that is our expectation. In order for the galaxy to grow to the size it is at distances closer to us, of course, in order for the galaxies to evolve into very massive and very impressive kinds of galaxies, they would need to have had reservoirs of cold gas. So we need to find that. We need to find a way to
Yeah,
detect and observe
right.
that reservoir and those reservoirs in the galaxies. Yeah.
So we're kind of saying, okay, well, galaxies now in the universe are big and they've got lots of gas and lots of stars. So, well, they must have had a load of cold gas in the past in order to have formed those stars. But then if they also had these black holes putting all of this energy in, destroying the cold gas, then they must have had cold gas earlier than that. So where is the cold gas? We're trying to find it, right? Where are you?
Exactly. That's the quest at this point.
Okay,
Yes.
okay. So you're pushing to even higher distances, so infinity and beyond, right?
Exactly. Yes, so when the universe was way, way younger than it is now. Yes.
Yeah. Okay. And so I have so many questions. I'm going to wrap it up now, I promise. But do you use just radio telescopes to look at this, or can you use anything else?
So as far as cold gas goes, the best way to observe is, yes, with the millimeter light, which is detected using the millimeter interferometers.
Okay. So, and that's all talking about the cold gas in the galaxy, which has the potential to form stars. But then you also mentioned this kind of warm gas around the galaxy. What's that, and how do you study that?
Yes, so the warm gas around the galaxy, that is the light that you get from atoms which have lost their electrons. So we call these, you might know from chemistry or physics, ions. Any atom that has lost one or two electrons becomes an ion. And when these ions recombine with electrons, or when the electrons within the ions skip down and up to different energy levels, you get emission and absorption. So you get light being added, coming out, light coming out from the source, or light being taken away. So in our case, we were looking at the light that comes out as a result of the ions coming together with electrons, or electrons skipping down to low energy levels in the ions. And this generally tends to happen in what we call warm gas component. And by warm, very different to our understanding of warm. Definitely not 24
So,
degrees Celsius.
okay, so not like a cheeky 30 degrees.
No, definitely not. It's more
Okay.
like 10,000 Kelvin. Excuse me, more
Okay.
like 10,000 degrees Celsius. So,
Wow. Okay.
so
So well beyond our comfort zone.
yes.
Okay.
So in these regions, yeah, gas that is kinematically more active. It's fast moving gas relative to the kind of slow moving gas that you would have in the cold component, where stars are forming essentially as a result of the cold gas reservoirs. But this ionized gas component, this warm component, is very important because it allows us to trace which parts of the interstellar medium, as well as the circumgalactic medium, have been impacted by radiation from the star forming regions, and also radiation from the supermassive black hole region. So, all of that radiation comes out and essentially heats up the gas, resulting in it becoming ionized. So, when we observe the ionized gas, we're able to understand how different parts of the the galaxy, different components are affecting the surrounding gas in terms of its temperature and speed.
Yep. So, okay, so it's like it's all about trying to understand where all the matter is in the galaxy and what state it's in and what it's doing and how it got there, right?
Exactly, yes.
So this is the full picture of trying to understand galaxies and what on earth they are doing and how they evolved. You put it really nicely. So this is in astronomy speak, but I just wanted to repeat what you said to me earlier. You're looking at for a consensus on the baryon budget in the circumgalactic medium. And I love that. It's so concise. And so I think I'm going to try and explain what that means and you'll tell me if I'm wrong. So you're trying to have a full understanding of where all of the matter is in and around the galaxy, right?
Yes.
Yeah.
Where it is and how hot it is, how fast moving it is, and essentially what the different proportions are of the gas that is cold and slow moving and the gas that is hot and fast moving.
Right. Okay, so can you leave some questions for us to answer, please, Sthabile? You're answering everything.
Okay.
I'm kidding.
Yes.
I'm kidding.
I was about to try and answer that. Okay, no, I can't. Actually, yeah.
All right. Well, thank you so much for speaking with us today. It's been a real pleasure. And do you have any final messages for listeners before you head off?
Yes. Whenever possible, if you are interested, look out for citizen science projects where you can sign up, register as a member of the public, and participate in real science, such as classifying galaxies by eye and helping us understand our data and our observations before we've been able to develop robots or machines that can help us understand our data. So we need your help and we need you as much as possible. Please try to dedicate your time to becoming a citizen scientist.
Yes, that's awesome. Thank you for saying that. And I think there's even new citizen science projects happening with South Africa's Meerkat telescope now.
Yes, I believe this is about gamma ray bursts. And in fact, there'll be
some sort of bursts coming from space.
Gamma ray bursts. Okay, yeah, some bursts from space. And we need a way to fish out where the real signals are from space and where they are not, perhaps signals that are not due to gamma ray bursts and that type of thing. So we need you to help us classify the objects.
There's too much work for all of us,
yes,
so help us. Mm-hmm. Okay, thanks very much, Sthabile. It was great to talk to you.
Okay, great. Thank you, Jacinta. It's great to be here.
Oh, wow, Jacinta, you sounded so excited when she was talking about visiting the ALMA construction.
Yeah, so we chatted over Zoom and I showed Simi the video of the interview and she was just laughing her head off at my facial expression when Sthabile was talking about...
You could not help it.
Well, it's exciting. Yeah, seeing a big telescope being constructed is very exciting.
Yeah, I mean, I think I also saw your excitement recently with the SKO. So literally, that is just a genuine expression that you have.
Well, I hope it's coming across on the microphone.
Yeah. So, Jacinta, have you been to a construction before of a telescope?
No, actually, yes, but not the SKAO. So that was just the construction commencement ceremony. So it was just a ceremony, really, before construction commences. But, being here in South Africa, I guess we've got a chance to go and hopefully see some of the construction of the SKAO at different points. Mm-hmm. But I have actually been to the construction of the LOFAR telescope.
Ooh.
Yes, most of LOFAR is built in. It's a radio telescope, a very low frequency radio telescope. So the antenna don't look like these dishes. It looks like these kind of almost like the metal Christmas trees, but not really. Like they look like poles with like this round thing on the top. And it doesn't really look like what you would imagine a radio telescope to look like. But it is, and most of those antennae are in the Netherlands, but some of them are in other European countries. And I happened to be visiting Oxford when I was a PhD student in the UK, and I got to go to one of the sites of some of these antennae and help on the very final day of construction. And my role was very technical. I had to stick the barcodes on each of them.
Look
antennas.
at you
Yes.
doing the most important job.
Sticking the barcodes, and I did it so well, Timmy, so I tell you. Yeah, so that's the only construction that I've seen, but yeah, it's always exciting. New telescopes, fresh data.
I'm excited to see probably the SKA. Yeah, I look forward to that actually.
Yeah, it's going to be really exciting. Cool. All right, well, I think that's kind of the end of the science bit today. So I guess before we end our episode, we always ask each other, how are you, Zimiso?
I'm good. It feels like things have just come down.
Calm down a little.
They just feel like they've come down a little.
Oh, good.
So that's good. But at the same time, very, very exciting things are going to be happening. And I'm preparing for that.
Okay. Can we talk about them yet or no?
No, not yet.
Not yet.
But
Okay.
probably in the next episode.
Oh,
when things
that's
are finalized.
exciting.
So we'll
okay.
see about that.
To be continued.
Yeah. And how are you?
I'm good. Quite tired, quite stressed and overworked. This is probably my busiest time of the year. I'm teaching, as I think I've said in previous episodes, I'm teaching the third year undergraduate course in galactic and extragalactic astronomy. And this first half of the course is content that I've never taught before. And so I first have to learn it and then teach it the next day. And it's every day, Monday to Friday at 9 a.m., which most people are going to laugh at me, but that is so early for me. I'm like a typical astronomer. I don't like early mornings.
I understand. I mean, I start at 10.
Yeah, so it's been a lot of work. But I think once I do it the first time, it should be easier next year and the year after that. So yeah, it's been busy, but it has been good. I really enjoy the teaching. The students are great. They ask so many good questions. They ask me questions that I don't know the answer to all the time. And when they do, I give them a Cosmic Savannah sticker as a reward. So.
I mean, that's a nice way to be encouraged, right?
Yeah. All right. Well, we've prattled on for long enough, so I think we'll end it there. So that's it for today. Thanks very much for listening, and we hope you'll join us again for the next episode of The Cosmic Savannah.
You can visit our website, thecosmicsavannah.com, where we'll have the transcript, links, pictures, and other stuff related to today's episode.
You can follow us on Twitter or X, Facebook, and Instagram at Cosmic Savannah. That's Savannah spelled Savannah. You can also find us on YouTube, where audio-only episodes are uploaded with closed captions, which can be auto-translated into many different languages, including Afrikaans, isiXhosa, and isiZulu. And maybe even we might have some pictures on our videos coming up soon, maybe.
And special thanks to today's guest, Dr. Sthabile Kolwa from the University of Johannesburg, for speaking with us.
Thanks to our social media manager, Sumari Hatting, our audio editor, Jacob Fine, Mark Allnut for music production, Michal Werchek for photography, Carl Jones for astrophotography, and Susie Karras for graphic design. Thanks also to Francois Camphor for assistance with the blog, and to Emil Menkis, Moses Mukungo, and Abigail Chanay for transcription.
We gratefully acknowledge the support from the South African National Research Foundation, the South African Agency for Science and Technology Advancement, the South African Astronomical Observatory, and the University of Cape Town Astronomy Department.
You can subscribe on Apple Podcasts, Spotify, or wherever you get your podcasts, and we'd really appreciate it if you can rate and review us and recommend us to a friend.
We'll speak to you next time on the Cosmic Savannah. Boom, boom, boom.